So let's have an example that illustrates the use of hypothesis testing in order to make an inference about the population mean. So here what do we have? We have in a department store, a manager wants to they want to install a certain billing system, okay, for the credit customers. Now, the problem with that system is costly. But however, it will be cost effective only if the mean monthly account is more than $170. For all their customers. So the population mean is greater than 170. So what they did in order to find out whether on average all their customers they spend more than 170, they collected sample of 400 customers. So they looked at their accounts, so 400 customers, and they found that they have an average of 178. So the question is that large enough to prove what they have in mind? And what they know also, they know that the standard deviation of all the customers' accounts is $65. So can we conclude that the new system will be cost effective, meaning that can we conclude that mu is really greater than 170? So this is what we're going to do in the next slides. We're going to use the hypothesis testing procedure. All right, so as we said before, the system will be cost effective really only if the average of all their customers' accounts is greater than 170. Okay, so this, by the way, remember I told you previously that this can be a challenging part in developing the hypothesis. The value of that mu that you're trying to find, whether it's greater, less, or different, how to come out with that. Look, in this case, it's very clear for us. This system will be cost effective only if the mean account is greater than 170. So it's not really hard here to find that mu naught, right? That we talked about before. So now we are able to develop the hypothesis. So my research question, or my question, the managerial question in this case is what? I need to find, because I need to make a decision whether to buy that system or not. Is mu greater than 170, right? So this is my alternative hypothesis. It represents the question that the manager has in mind or the researcher has in mind. Once you have the alternative hypothesis, then the null hypothesis comes automatically, right? Because we said if I have a mu here, I will have a mu in the null hypothesis. This value will be seen there, and always the null hypothesis, I have the equal sign. So here we go. All right. So always focus on finding that, on developing your alternative hypothesis. The null hypothesis comes automatically. Okay, so what do we know? Now that we have the hypothesis, I have collected an evidence, right, from the sample. We found that the sample mean is 178. So now the question is 178 sufficiently greater than 170 to allow us to infer that yes, nu is greater than 170, and this will allow us then to reject our null hypothesis? Now you see here it's not clear for us. It's not like the previous example when about the economist, where he's looking whether mu is greater than 14,800 and we found x bar to be 30,000. That's much larger than it was, really unquestionable. But here it's not clear for us what to do. So we need to find a certain criterion. What's that criterion? We cannot leave it to subjective judgment. We cannot do that. We have to have a criterion, and luckily there are two criterion. In fact, there are two approaches that we use in hypothesis testing. The first approach is called the rejection region approach, and second one is called the p-value approach. Now, there are similarities between these two that I'm going to emphasize later, but for now, we're going to start with the rejection region approach, the first one, and I'm going to show you how to come out with such criterion, and then I'm going to guide you through and I'm going to explain a much simpler method using that rejection region approach. So let's see what's happening there. All right, so we are looking for a value such that if the sample mean is greater than that value, we will say that, all right, it is large enough, so it's supporting our alternative hypothesis. Okay, so, and this is the value that we are looking for. What's that large value, right? So this L is for large value, such that it will give us confidence that, all right, if the sample mean is greater than that, we have collected that evidence. Let's see graphically here what's happening. All right, so remember we are starting from the assumption that HO is true, and when we say HO mu is 170, so we put that 170 in here. So if HO is true, that means the X bar that I collected, as I showed you in the previous illustration, belongs to that distribution. All right. Now, I'm looking for an X bar L, a large value of X bar, such that if a sample was found to be greater than that, I will say, all right, it is large enough. But what's that value? How can I find that value? This cannot be random, but instead I'm going to use the knowledge about the type 1 error, alpha, right? We have already defined alpha, okay, to be the probability of type 1 error. So yes, I'm acknowledging that sometimes I will reject a certain a null hypothesis while it was true. So I'm going to build on that. Okay, so I'm saying that, all right, alpha is the probability that type 1 error, I'm doing a type 1 error. And when do we do type 1 error? When we reject HO, given that HO is true, which means this is true. This is still valid. No X bar belongs to that distribution, and I'm rejecting that. When do we reject that? Look, here we go. It's showing you. This is when we reject, this will be the area where we will be rejecting our HO. So I'm saying that if I find a value of X bar to be in that area, I will reject it. This is a calculated error. I know the probability of that error, and I can use that in my contingency plans. Okay, so in other words, alpha is what? It's the probability that X bar is greater than X bar L, right? So if X bar is greater than this, I will be rejecting my HO, but I know that this may be a type 1 error. So I'm going to use now this statement to find my X bar L. And I'm going to illustrate for you that in the next slide. So let's see how we're going to find that X bar L. In fact, what you're going to see in the slide is these are all steps that you have learned how to do in the previous topics. All right, this is what I was repeating many times, that if you have a good foundation about normal distribution, about sampling distribution, then the inferential statistics method would become, the technique of the inferential statistics method becomes easy for you. The concept, yes, of course, it's a new concept. Once you grab this concept, the technique is easy for you because you have already learned about that. All right, so we ended the previous slide with that equation, right? This relationship between alpha and the probability. Alpha is the probability that X bar greater than X bar L given that HO is true. Okay, so what do I do next? We standardize as we did before. So I will subtract in each side of the equation, I will subtract mu and I will divide by the standard deviation. So I do that on both sides of the inequality. And on this side, I will end up with Z. On the other side, okay, this is a value. I don't know it yet, but it's a value. So our also replace that mu and standard deviation, and I'm saying that this is equal to alpha. All right, but how this is going to help me to find my x bar L? Look at this. I'm saying that P of Z is greater than a certain value. Remember, this will be, after all, when I find x bar L, it will be a value, is equal to alpha. But I know from the Z table, okay, that if I know alpha, okay, I can tell what's a value of Z such that P of Z is greater than that Z is alpha. And remember, we denoted that by Z alpha. What's Z alpha? Remember, we said GA also. Here we go. This is Z alpha. We have used it in the confidence interval estimation, right? So this is alpha. And I can find that, right? Because if I know that this is alpha, that means this is 1 minus alpha, and I look up in the table, I can find Z. So I have here a Z, and I have there in the upper part a value that contains x bar L that's unknown yet for us. Here I have alpha, and here I have alpha. So what does it mean? That means these two values that I circle, they are equal. So x bar L is unknown. Mu is known because this is assumed to be true. This is known, this is known, this is known. So now we can solve for x bar L. Okay, so let's find now x bar L and finish this exercise. Okay, as I said before, we are assuming HO to be true. And this is very important, otherwise I cannot proceed with the hypothesis test procedure, right? So we are saying that mu is 170. So I replace that 170 in the previous equation. And I know also that for alpha is 5%, Z that has a area on the right hand side equal 5%, we denoted by that, it's 1.645. This is something that I hope that you know now by now how to do that. Okay, so replacing these values in my previous equation, which is this one. Okay, now so mu is 170, assumed to be true. This was given to us. This is our sample size that we decided to make, and this is our Z. So now what we do, we solve for x bar L, and we find that the large value of x bar that will give me confidence that if I find a sample mean greater than that to be enough evidence to support my alternative hypothesis that's saying that mu is greater than 170. Here we go. It's 175.3. Okay, I will call that, if you want, my cutoff point. Okay, I'm going to use that term a lot also. So here we go. This is 175.3. So when I collect a sample from this population and I find x bar to be anywhere here, then I reject my null hypothesis, and that's why this approach is called the rejection region. This is a rejection region, all right, RR, rejection region. So here we go. In our case, the sample that we found was 178, greater than the critical value. Okay, x bar L, we call it the critical value or the cutoff point. Okay, so what do we say? We reject the null hypothesis. And this is in favor of our alternative hypothesis that say mu is greater than 170. And then we conclude then we always finish our test by interpreting the results in the term of the original question. What was the question? Is that system cost effective? And now we are saying yes, it is cost effective because we have answered our alternative hypothesis that was reflecting this managerial question, and it can be also a research question. All right, so I hope that was clear for you how we found that cutoff point, the critical point, the x bar L. And I have good news for you. that you will not have to do that exercise yourself. You will not be finding X bar L. But understanding what we did is very important for your understanding for the concepts underlying, okay, our rejection region approach. And I'm going to show you a very, very simple method how to use the rejection region approach.